Inferential statistics. So after you have a general knowledge of the descriptives as well as quantitative research method, we proceed to the inferential statistics, which is built on top of descriptives, but it gives you a explanatory power to explore the causality instead of the observation of the trend over a series of data. So basically what I'm saying here is you could estimate a difference, you could estimate a causality with inferential statistics. Okay, before we could get to the actual method that you could use to test your differences or causality, we need to talk about inferential statistics in general. We will focus on the comparing groups techniques. But before that, you need to understand that there are two different families or categories of inferential statistics. Well, there are other categories, but we will focus on the parametric and non-parametric techniques. So parametric techniques include a long list of technique approaches such as t-test and one-way ANOVA. So parametric tests basically have a assumption of things such as normal distribution, interval scaling, but it estimates along with the probability, the p-value, also the parameters, where non-parametric techniques lifted those assumptions of the population distribution, but it still present the power of probability, so the p-value. The only difference here is basically the parameter is not interpreted as the parametric techniques. You've downloaded this data set already. If you haven't, then I advise you to do so. It's a complete version of the Survey 5ED short data set we've been using. And this data set is in the format of .sav, which is basically SPSS data file. After you download it, you could click on it and look at variable view, explore the different techniques. So for this discussion or for this module on SPSS, we will cover mainly three different types of comparing groups techniques, but these are really important and very commonly used techniques. The first one is the chi-square test. Second one is t-test, but more specifically, it's actually independent sample t-test. And the third one is one-way analysis of variance, or also called the one-way ANOVA test. So these tables here actually are examples of each of these tests. So on the first row, these different columns are actually the categorical variable that is acting as the independent variable in this case, where we have the first column, the two rows are the categories of our dependent variable. Same thing applies here. Male and female is a categories of the independent variable, or life satisfaction score is the dependent variable. And same here, age group 1, 2, 3 are the categories of independent variable, and life satisfaction score is the dependent variable. So you can see already that the difference among these tests Well, the first thing, let's talk about similarities before the difference. Similarities are, you can see that independent variables are categorical. So the first independent variable is gender, second one is gender as well, third one is age group. Okay, so all the independent variables are actually categorical variables. Then for the dependent variable, that's where the difference comes in. The first one, chi-square test, dependent variable is categorical. For the t-test, the dependent variable is actually continuous. It's life satisfaction score. And for the one-way ANOVA, the dependent variable again is continuous, which is a life satisfaction score. Another difference comes in if you look at how many categories are there in the independent variable. For the previous two, the chi-square and t-test, there's 2. For the one-way ANOVA, there's 3. And later on, when we look at each of the test modules, you will know that for chi-square test, it doesn't matter. It doesn't matter how many categories are there for both dependent and independent variables, independent and dependent variables. But for t-test and one-way ANOVA, the major difference is that t-test only allows 2 categories for your independent variable. So some people even say that t-test is actually a very specific case of one-way ANOVA with just 2 categories for independent variable. Okay, but you also remember that we talk about parametric, non-parametric. That is because for each parametric test, you have a corresponding non-parametric test. That is in case that the normal distribution, for example, is not fulfilled. So chi-square test by itself is non-parametric, so there's no parametric comparisons here because chi-square is comparing 2 categorical variables. There's no continuous variable involved, so in that case, chi-square is just a non-parametric. But for independent sample t-test, if, for example, your dependent variable is not normally distributed, then you need to use a non-parametric corresponding technique, which is called Mann-Whitney test. You could actually run this test with SPSS as well. We are not covering the techniques of Mann-Whitney or Kruskal-Willis of the basically non-parametrics corresponding to T and one-way ANOVA in this module, but I could quickly demonstrate without mentioning too much of the background of these 2 tests. Then similarly, for one-way ANOVA, you have Kruskal-Willis test, which is the corresponding non-parametric test for one-way ANOVA. So let's look at those assumptions that actually separate the parametric with non-parametric, separate the parametric to non-parametric tests. There are 5 assumptions, but the previous 3 are very common ones. So these are assumptions for parametric techniques. As long as you fulfill all these 5, then you're fine. But these 3 are very common. Let's look at the first one. Which is dependent variable should follow interval or ratio assumption, which means equal distance between each group. So your dependent variable should have a equal distance among each observation, which is, in most of the case, is how you collect your data. Second one is random sampling. Well, 150 plus of sample size. In majority of the case, that's how it's been collected. Well, random sampling. Well, in this module, we don't cover the sampling techniques, but random sampling basically means that as long as the randomization has been done on a categorical level, or what people say stratified randomization process, then you're fine. independent of the observation assumption is basically that your samples are independent from each other, which is most of the case, but of course there are cases that your samples are influencing each other. The most important one are assumption 4 and assumption 5. And assumption 4 is the normal distribution assumption. So when we talk about distribution histogram, we talk about a bell-shaped distribution, and that is the normal distribution assumption for your dependent variable if you're going to use parametric tests. If the normal distribution is not fulfilled, then you need to use the corresponding non-parametric techniques, that is either Malvina U-test or cross-covariance test. The fifth assumption is actually homoscedasticity. So homoscedasticity assumes that the sample obtained from the population of equal variance. There are multiple ways of assessing this, but for the purpose of this module, just bear in mind that as long as you have a large enough sample, that is 150 plus, you could leave this restriction, or you could just choose to not to pay too much attention to this assumption for now. Well, if you're researching for high-level publication, then people might ask you to plot homoscedasticity, and you might need to have means to correct for heteroscedasticity. But again, majority of the case, if you have a decent size of sample, then it could be relaxed in terms of this assumption. So that's well, okay. Last bit before we actually look at how to do each of those tests. That is, familiar yourself with the terms and notions that I've used. So for all the parametric and non-parametric, we will generate something called a statistic significance in our test result, which is the probability value p-value. And the most general rule of thumb here is that we use the cutoff point of 0.05 as a level. So any p-value smaller than that, we will reject the null hypothesis of no relationship or no difference, and accept the hypothesis of a difference or a causality relation. But you could shrink this down to maybe 0.01 or even 0.001. But the test result will report a p-value for you. And the cutoff point is, well, you have actually techniques to decide your alpha value, but it's not, it's beyond the curriculum. Again, here you just need to remember that the most often used p-value cutoff point is at 0.05. What does this mean though? It means that you have a 5% chance of accepting falsely of the hypothesis 1. Okay, so there's a 5% chance that your acceptance of H1 hypothesis 1 is actually wrong. But we're talking about probabilities here. We're not talking about you're definitely right or definitely wrong.